150. 0.3928 meter cube per kilogram for the first case. For the second case, temperature is 320 Celsius, pressure is 20 bar. For third case, temperature is 100 Celsius, and enthalpy is 2,100 kilojoules per kilogram. Case 4, pressure is known as 60 bar. Specific volume is 0.025 meter cubed per kilogram. This is for properties of water. Okay, so we know our substance, we know our pure substance, and we go to table for water, which is table A2. Okay. If you look at your known properties, temperature, in this case, temperature and specific volume, if you go to guideline that I gave you in the previous lecture, you will see that for a temperature given, you go to temperature as a temperature related table, which is table A2. Okay, everyone? Okay, good. For 150 Celsius, okay, you have a pressure, saturation pressure is 4.758 bar. Did you see it? Okay, but that is a saturation pressure. We don't know if our pressure for this case is that pressure. In order for us to determine that, we need one more property, which is given specific volume, 0.3928. At table A2 at 150 Celsius, right? Our specific volume is what? 0.3928 exactly, right? On a saturated vapor line, which means that our pressure is saturation pressure given at the table. So we can write 4.758 bar. Okay?
You said that was saturation pressure?
Saturated vapor.
With vapor pressure? No.
Yes. The saturation pressure. Okay, maybe. Okay. Temperature, pressure, right? Saturated liquid, saturated vapor. Remember that line I gave you on a PV diagram? Okay, PV diagram. This line was a saturated vapor. Left line was saturated liquid, correct? Critical point, wet vapor, compressed liquid, superheated vapor, right? So in this table, right, saturated vapor and saturated liquid values are given. So when we check at this temperature for specific volume given at 0.3928 meter cube per kilogram, I found out that my phase is saturated vapor. Okay, for saturated vapor, properties of saturated vapor table. Okay. So for that temperature and specific volume, I found out that I can use saturation pressure given at the table because of my phase. Okay? We will solve other examples here. Okay, so in this case, I can easily use the value given in the table because I'm in the saturated vapor region. So I can take all internal energy, enthalpy, entropy, specific volume at a saturated vapor region. Okay, so at 150 Celsius, right? Specific volume, internal energy in this case will be 2,559.5 kilojoules per kilogram. Enthalpy will be 2,746.5 kilojoules per kilogram. Okay. What was X? X was a quality factor, right? Quality factor, maximum is 1, right? Minimum is 0. If you find something less than 0 or more than 1, you did it wrong. So check, okay? It's impossible. So in this case, our phase was saturated vapor, so the quality factor will be 1. Okay? All right. Second case. I'm given temperature and pressure. Okay? 320 Celsius, 20 bar. For 20 bar, my saturation temperature 212.4 Celsius, right? My temperature exceeded that saturation temperature, which means I'm in superheated vapor region. Okay, I go to superheated vapor table, table A4. Okay, 20 bar. 20 bar. 320 Celsius. You read the values. As you can see, you don't have all the temperatures here. If you had 323.8, what would you do? You would do linear interpolation. Okay, you will interpolate each of these columns. Specific volume, internal energy, enthalpy, and entropy. Okay, so in this case, it's easy. It's given. We have the exact temperature, 320. So I can write this. Specific volume, 13.8 meters per kilogram. Internal energy is 2,807.9 kilojoules per kilogram. Enthalpy is 3,069.5 kilojoules per kilogram. Right? For case 2, I'm left with quality factor. What is my quality factor in this preheated region? Not exact. It cannot be defined. Right? Case 3. 100 Celsius enthalpy is given 2,100. 100 Celsius, right? 100 Celsius enthalpy. Saturated liquid 476.04. Saturated vapor 2,676.1 reduced per kilogram. I'm in between, which means that I'm under the saturation curve, right? 2,100 in between. So my pressure, the saturation pressure, 1.014 bar, right? I know my enthalpy. I need to calculate my specific energy, specific volume and internal energy, specific internal energy. Right? But first, I need to calculate my quality factor, what my quality is. Remember how we calculated our quality. X equals V minus, if you know the specific volume, Vf, Vg minus Vf equals, if you know internal energy, equals U minus U sub f divided by Ug minus Uf. If you know enthalpy, right? H minus Hf divided by H T minus Hf. You know entropy, S minus Sf, Q minus Sf. Right? So if you do this, what is my quality factor? Could you tell me? (2,100) minus 419.04 divided by 2,257 to give you 0.7448. Okay. Once you find out your quality factor, from here, you know your quality factor now. You know your specific volume as saturated liquid. You know your specific volume as saturated vapor. You know your specific volume as saturated liquid. Right. Only thing you left with your specific volume at this particular case. Right. You can calculate that, and you should find, please find these things: 1.2463 meters cubed per kilogram. And same thing for internal energy. You know your quality factor is same, 0.7448. You know your internal energy as saturated liquid. You know your internal energy as saturated vapor and saturated liquid. You can find your U, internal energy, which is 1,973.73 kilojoules per kilogram. Okay. Case 4, 60 bar pressure and specific volume is 0.025 meters per kilogram. Okay. Table A3, if you go to 60 bar, okay, 60 bar, right? You check your specific volume problem. Saturated liquid and saturated vapor value. Saturated vapor value is 0.03244 meters per kilogram. saturated liquid value 1.3187. But there is something you should careful here. Saturated liquid specific volume value is multiplied, pre-multiplied by 1,000. Okay? So you need to divide this value by 1,000. Okay? This is 0.001318. All right. So in that case, you are in between again. Right? So using quality factor calculation to find your quality factor, temperature, internal energy, and enthalpy. You don't need to calculate your temperature. The temperature in this case is the saturation temperature since you are in the saturation curve. Okay? 275.6. Quality factor is 0.7609. Internal energy will be 2,258.76. Enthalpy will be 2,408.77 kilojoules per kilogram. R22. Make sure you find the case 3 and case 4 by yourself. You should be able to find these values for each case. Okay. Now this is for substance R22. It's a refrigerant 22. You should have a table for that as well. Okay. What we're going to do here, I will give you what I did for this table, but after this class, you will complete the table. It's just for practice. Case 1, again, pressure is 1.5 bar. Specific volume is 0.00073 meter cubed per kilogram. Temperature for the second case is minus 32.08 Celsius. Pressure is 1.5 bar. Case 2B, pressure is 1.5 bar. Internal energy is 214.77 kilojoules per kilogram. Case 4, pressure is 1.5. Internal energy is 100. I will give you the answer for the next one. Any questions?
So you said that the values on the table have to be divided by 1,000,
Not all of them, just
just,
specific volume and saturated liquid. Celsius multiplied by 1,000.
They're on scale.
Just for scaling. Shall we move on? All right, now let's solve some problems. Let's see how we apply these table skills on a problem, right? Example. Saturated liquid water contained in a closed rigid tank. Is cooled to a final state where the temperature is 50 Celsius. And the masses of saturated vapor and liquid are 0.03 and 1,999.97 kilograms respectively. Determine initial temperature. In Celsius. The volume of the tank in meter cubes. Heat transfer kilojoules. Last but not least, sketch the process on a P2 diagram. And it will be done. All right. It's a closed system. Closed system, and I have a water as a pure substance. Right? What was pure substance? Pure substance is a substance changes phase under certain conditions. Okay? From compressed liquid to superheated vapor, or wet vapor to saturated vapor, or from superheated vapor to compressed liquid. Okay? Depends on the condition. In this case, we have a saturated liquid vapor to water contained in a closed rigid tank. Have a tank closed rigid tank. rigid tank. And have H2O, the pure substance, right? Boundaries of my system where I'm interested, right? Where my mass is trapped. I need to show the boundaries. All right, for state one, I say we are moving from one state to a final state, right? I have one process. Two states, I have one process to move from one to another. Okay? I'm given some conditions that state one, the saturated liquid, right? Temperature, mass fat and volume at state one. Meter cubes in Celsius, mass fat, right? The final state or state two, you can call either or final. Right? Temperature given 50 Celsius. Liquid and vapor mass ratios are given. Liquid mass 1,999.97 kilogram. Vapor is 0.03 kilograms. Okay. So state one. My quality factor is what? 0. But at state two, it's somewhere in between because I have a mixture. All right? All right. We've talked about a couple processes in thermodynamics that we will be often using from moving from stage to states, right? Which were isobaric, isometric, right? Isentropic, adiabatic, isenthalpic, etc. So in this case, what is my process? Usually, and mostly, you are not given the process, name of the process. As an engineer or a solver, you need to figure out what your process is from the problem statement. Okay? By using your common sense, right? In this case, I have a rigid tank. What does it mean?
Constant volume.
Constant volume, right? My process in this case will be isometric. Right? So volume one equals volume two, or specific volume one will be equal to specific volume at state two or final state. Okay. Again, because it's a rigid tank. X, quality factor, the final state. I know my mass ratios, right? I know my mass, like gas form or vapor form, and I know my total mass. Okay? So remember, when we define quality factor, we define as a fraction of masses, right? In a vapor form. So mass in the gas form divided by the total mass will give you the quality factor. Okay? What was it? And vapor into liquid plus gas. Right? will be specific volume. And Fox factor times difference between specific volume, saturated vapor minus saturated liquid. Total volume. I know my mass, and once I calculate my specific volume, I can calculate my total mass. Total mass, total volume. Sorry, total volume it will be mass times specific volume. Right? And of course, first law of thermodynamics. Because I'm constantly calculate heat transfer into the system or equivalent system, cooling or heating, cooling. All right, that's all. So my total mass and liquid plus and gas equals 2000, right? So Quality factor at state 2. 2.03 kilogram over 2000, 1.5 times 10 to the minus 5. Right? I know my quality factor at state 2. I can read my specific volumes and saturated vapor and saturated liquid from the table at a given temperature or pressure at a given condition. Right? By using quality factor calculation, x equals V minus Vf divided by Vg minus Vf, right? If you take the unknown out, what we have is V specific volume plus x2 V minus F. If you substitute all those knowns, you can find out to be able to find your specific volume at state. Okay? So, fine. Specific volume at state 2. Where's my specific volume? Saturated liquid 1.021. Let's read it. If you go to table A2, you go to table A2 at 50 Celsius, that's my temperature of final state. 50 Celsius, saturated liquid, saturated vapor, 1.01. Yes. Times 10 to the minus 3, right? Remember that times 10 to the minus 3 or divided by 1,000.
Is it 1.021? 1.
You can put 1. Divided by 1,000. Okay. Meter cube per kilogram. I just calculated my quality factor, 1.5 and 10 to the minus 5. Right? Specific volume of saturated vapor is 12.02332 minus 1.0121 times 10 to the minus 3. You should have specific volume at 1.193 times 10 to the minus 3 meter cube per kilogram. Okay, now I have my specific volume at state 2. Right? Now I'm ready to calculate volume of the tank. Volume, mass times specific volume at state 2. Right? I know my mass, I know my specific volume, and I should repeat it. Volume will be (2,000) kilogram times 1.193 times 10⁻³ meters cubed per kilogram. We have 2.385 meters cubed. Okay. I'm still at state 2. I'm still at a final state. I haven't moved to state 1 yet. And I need a connection to do that. What was that connection? Isometric, right? I know specific volume at state 1 equals that specific volume at state 2. But isometric, correct? So which is 1.193 times 10⁻³ meters cubed per kilogram. Okay. And Bob's factor is 0 because saturated liquid, right? All right. Okay. Remember what state postulate states. If I know two properties, I should be able to determine the rest of the properties, right? We said this, we defined this in the previous lecture. And I have two properties here, right? Specific volume and a Clausius factor, right? You go to table A2, right? Search for specific volume, value is 1.193 times 10⁻³. Okay. 1.1 9.3. It's here, very close. 1.19 times 10⁻³. Okay, that equals around 220 Celsius. If you want an exact value, you can interpolate and find the temperature you want, right? It should be 1.20 point something, but very close. From table A2, right? Temperature will be 220 Celsius. Okay.
So when it's very, very close, you can choose calcium surgery, or should you avoid surgery?
It's better to interpolate, but if it is this close, you can approximate. Okay? You will see some examples. In the future, we will be using 4, 5, 6 processes. And when you don't interpolate and when you don't have an exact value, it accumulates and it gives you off result at the end. Okay? All right, let's continue. All right, right, I know my temperature at state one now, and I need my internal energy, entropy and enthalpy. I can find whatever I need, but I need internal energy in this case, because I'm off to calculate heat transfer in kilojoules. Okay, so it will be 940.87 kilojoules per kilogram, right? At temperature 220 Celsius, it will be 940.37 kilojoules per kilogram. Okay. And U2, internal energy at state 2, could have found it beforehand. I can find it now as well, right? Because I know all the other properties that I need. Fine. So my temperature at state 2 is what? 50 Celsius, right? And I have Coiled factor 1.5 times 10 to the minus 5. Okay. U2 will be UF of X2 U minus UF. I know my UF, I know my X2, I know my UG and UF. So I can find my U2. U2 will be 209.32 kilojoules per kilogram is UF plus 1.5 times 10 to the minus 5. 2,443.5 minus 209.33 kilojoules per kilogram. U2 will be 209.35 kilojoules per. Okay. So I have everything I need for this problem now. First of all, family analysis. Okay. What is work? Work is 0. Why? Because it's a rigid thing. Remember work. Work equals P times delta V. My delta V is 0. So work is 0. Okay? Q from state 1 to state 2 will be only equal internal energy difference in the states. Will be M times specific internal energy difference. Or you can write it in this way, M times U2 minus U1. So Q, heat transfer from state 1 to state 2. The mass 2,000 kilogram times U2 209.35 minus U1 is 940.7 kilojoules per kilogram. Kilograms cancels out. And Q will be minus 1.4 It's 3 times 10 to the minus 6 kilojoules. Okay. We're also finding kilojoules. So we did. All right. One last thing. I'm asked to sketch this process on a PV diagram. All right. State 1 is somewhere around here. How do I know? Because it says the state 1 initially is associated with liquid, right? And the system is cooled down. Notice my heat is minus. Minus means what? Out. So it's cooled down. If it is cooled down and your heat is positive, you did something wrong. Being accurate, the key. Make sure you follow all the steps. If you miss one step, you approximate instead of linear interpolation, this will be off. Okay, that's state 1. This is state 1, right? How would it look on a PV diagram? How would you draw on a PV diagram? What is it?
Vertical line.
Vertical line? Okay.
That'll be a vertical line. I'll show you.
Right, vertical line because
Why is it not?
volume is constant. Right? And when I look at this, it's all makes sense. State 1 is in saturated liquid, state 2 is in wet vapor region. Yes. And volume doesn't change. Correct. Okay. Questions?
Yeah, linear interpolation, is that just like just pressure over values equal to the
We will do
something like what you're looking
We will make it. Yeah. I have enough time for another example. All right. Example. A piston cylinder device contains 5 kilograms of refrigerant 134A. The 1 and 1 at A bar and 60 Celsius. The refrigerant is cooled at constant pressure until its temperature is 20 Celsius. Determine. Heat transfer in kilojoules sketch the process line on a PV diagram. Piston cylinder assembly contains R24A, initially at temperature 60 Celsius and pressure 8 bar. Cool down. We'll have on A, temperature in this case is 20 Celsius, and pressure 8 bar. Right? Right. At state 1, temperature is 60 Celsius, pressure is 8 bar. At state 2, temperature is 20 Celsius, pressure is 8 bar. As you can tell, it's either process. Okay? Okay. Our first law of thermodynamics. Right? For state 1, table for refrigerant 124A. 4A. Sorry. Well, if you have it, you can check your saturation temperature at pressure 8 bar, right? Your saturation temperature should be 31.33 Celsius, correct? Right. So our temperature given at state 1 is 60 Celsius. So it's exceeded, it's over saturation temperature. So I boiled it and then I increased the temperature to put it in a superheated vapor region. So our case is superheated vapor. Right? So you go to superheated vapor table for refrigerant 134A. Okay. You go there, right? For pressure 8 bar, P1 60 Celsius, more than higher than saturation temperature, which is 31.33 Celsius. So it's a superheated vapor. A superheated vapor table, right? P1 at 8 bar, 60 Celsius. Right? The V1 will be 0.0 0.2992 meter cube per kilogram. U1 at 8 bar at 60 Celsius. Internal energy, specific internal energy will be 271.04 kilojoules per kilogram. Enthalpy, entropy, whatever you need, okay, you should be able to find. Enthalpy will be 294.98 kilojoules per kilogram. State 2. State 2. Less than saturation temperature, right? 31.33. Okay. Is compressed liquid region, right? You shouldn't have compressed liquid table for refrigerant 134A. If you have it, good for you. You can just read the values from compressed liquid table, but mostly you will not have it. As we mentioned in the previous lectures, you will not have compressed liquid tables. When you have those cases, you can approximate the saturated liquid properties at a given saturated property table. Okay? So, state 2, specific volume of approximately at 20 Celsius is 0.8157 times 10 to the minus 3 meter cubed per kilogram. Internal energy, right, at 20 Celsius. Remember, in the compressed liquid region, properties are only a function of temperature. Only a function of temperature. At 20 Celsius, internal energy will be 76.80 kilojoules per kilogram. Enthalpy approximately 77.26 kilojoules per kilogram. Work. Number work equals E EV. Would be P V2 minus V1. That's the constant pressure, right? Constant pressure is constant. I can take it out of the interval and prepare to specific volume inside the interval. P times V2 minus V1. Right? Work from state 1 to state 2. Pressure, right? M mass times specific volume at state 2 minus specific volume at state 1. Eight bar mass is given as 5 kilograms. V2 is 0.8157 times 10 to the minus 3 meter per kilogram. 0.8157 times 10 to the minus 3 meter per kilogram minus this volume at state 1 was 0.02992 meter per kilogram. 0.2992 meter cubed per kilogram. Okay. Which should give you minus 1.164 bar times meter cubed. But we are asked to find in kilojoules, so I need a unit conversion. 100 kilopascal, 1 bar. Will be minus 116.4 kilopascal times meter cubed. If you convert Pascal to bar, Newton times meter, and the pressure is Newton over meter square. We should have kilojoules from here. Okay. So it will be minus 116 times 4 kilojoules. Heat. Heat transfer from state 1 to state 2. M times U2 minus U1, right? Plus work from state 1 to state 2. So heat from Q from state 1 to state 2. I know my N, 5 kilograms. U2 is 6.80 kilojoules per kilogram. U1 is 270, 1.04 kilojoules per kilogram. Plus minus 116.4 kilojoules. Which is work we just calculated. From here, heat transfer minus 1,087.6 kilojoules. Q out, or you can tell Q out 6 kilojoules. From state 1 to 2. Okay. Let's define an enthalpy. Let's define H U plus PV. Right? It's a definition of enthalpy. And from here, I will show you that we can solve this problem by using enthalpy instead. So, in first law of thermodynamics, Q1 from from state 1 to state 2, number internal energy stored in the system M times Q2 minus Q1. Plus work interaction from state 1 to state 2, right? Work equals P times V2 minus 4 P times V2 minus V1. All right. If you take this into, and there's an n. And if you take this into common parentheses, right, and p2 minus p1 plus p2 minus p1. Right? u2 plus p2 v2 minus u1 plus p1 v1 times mass. The definition of enthalpy, right? I have an enthalpy to u plus pv, u plus p. Do that, P will be m times h2 minus h1, right? This is h2, this is h1. All right? So I found my enthalpy properties at state 1 and state 2 already. So I can insert them and find my heat. See if it gives me same. H2 is 77.26 minus 294.98 kilojoules per kilogram. Q from state 1 to state 2 will be minus 1088.6 kilojoules. It's pretty close, right? Okay. Last artificial material diagram. Actually, 4. State 1, state 2. Okay. You can write your V2, V1, and A4. Let me know if you have any questions. You have assignment due this Thursday, right, before class. Can upload on a Canvas, a single PDF file. If you have any questions, let me know. Have a good one. See you on Thursday.
Yeah.